Remember, continuity is all how nearby inputs are sent to nearby outputs. Differentiability is how wiggling the input affects the output. Now, in light of this, they seem related, right? Something like the following seems plausible. Here's the theorem. Theorem: if f is differentiable at a, then f is continuous at a. In other words, a differentiable function is continuous. Morally, we know that a differentiable function is continuous, but we're advanced enough at this point in the course to give a precise argument using limits. Here we go. Let's suppose that f prime of a exists. In other words, that means a certain limit exists. What limit? Well, the limit of f of x minus f of a over x minus a as x approaches a. This limit of a difference quotient computes the derivative of the function at a. So to say that the derivative exists is to say that this limit exists. Now here comes the trick. What I'd like to compute is the limit of f of x minus f of a as x approaches a. But I don't know how to do that directly. But I can rewrite this thing I'm taking the limit of as a product. Watch. Instead of taking this limit, I'm going to take the limit as x approaches a of x minus a times this difference quotient times f of x minus f of a over x minus a. Now, as long as x isn't equal to a, this product is equal to this difference. Now, why does that help? Well, this is a limit of a product. So by one of the limit laws, the limit of a product is the product of the limits as long as the limits exist. And in this case, they do. So this limit of this product is the product of the limits. It's the limit of x minus a as x approaches a times the limit of f of x minus f of a over x minus a. I'm only allowed to use this limit law because I know both of these limits exist. Now this first limit, the limit of x minus a as x approaches a, that's 0. And this second limit, well, this limit exists precisely because I'm assuming differentiability. The function's differentiable, so this limit is calculating the derivative at a. And 0 times any number is equal to 0. The upshot here is that we've shown that the limit of f of x minus f of a is equal to 0 as x approaches a. Why would you care about this? How does that help us? We know that the limit of f of x minus f of a as x approaches a is equal to 0. What that means is that the limit of f of x as x approaches a is equal to f of a, but this is just the definition of continuity. So now we know that f is continuous at the point a. That's where we ended up. Remember what we started with? We started by assuming that f was differentiable at a. And after doing all this work, we ended up concluding that f is continuous at the point a. So differentiability implies continuity. One way to keep track of arguments like this is to think about clouds and rain. Theorem: if it is rainy, then it is cloudy. A shorter way of saying this: rainy implies cloudy. Now the question is, does it go the other way? If it's cloudy, is it necessarily rainy? Can you think of a cloudy day with no rain? Yes, today. Let's look out the window. It is very cloudy, but there's no rain. Beyond clouds and rain, let's bring this back to the mathematics. A differentiable function is continuous. Can you think of a continuous function which isn't differentiable? You might want to hit pause right now if you don't want the puzzle given away. Here's an example of a function which is continuous but not differentiable. The function f of x equals absolute value of x. We recently saw that the absolute value function wasn't differentiable at 0. But how do we know that the absolute value function is continuous everywhere? We know that the absolute value function is continuous. I mean, look at it. It's all one piece. But we can do better. We can use our limit knowledge to make a more precise argument. We know that f of x equals the absolute value of x is continuous for positive inputs. It's continuous on the open interval from 0 to infinity because the function x is continuous there. And this function, the absolute value function, agrees with the function x if I plug in positive numbers. Likewise, I know that the function is continuous on negative inputs because the function minus x is continuous there, and the function minus x agrees with this function on this interval. The only sticking point is to check that the function's continuous at 0. And if I know it's continuous for positive inputs, negative inputs, and it's continuous at 0, then I know that it's continuous for all inputs. Now, how do I know that the absolute value function is continuous at 0? Well, that's another limit argument. The limit of the absolute value function when I approach from the right-hand side is the same as the limit of the absolute value function when I approach from the left-hand side. They're both 0. And because these two one-sided limits exist and agree, then I know the two-sided limit of the absolute value function is equal to 0, which is also the function's value at 0. And therefore, the absolute value function is continuous. In the end, there's some relationship between differentiability and continuity. Differentiable functions are continuous. Mathematics isn't just a sequence of unrelated concepts. It's a single unified whole. All of these ideas are connected at the deepest possible levels.